Hello, and welcome to this webinar presented by Radiant Vision Systems. And now I would like to introduce today's presenter. With us today we have Andrew Monroe, the Regional Sales Manager for Radiant Vision Systems. To read more about Andrew, please look at the speaker bio window right next to the main presentation window. And Andrew, welcome to today's event. And with that, I will pass things along to you to get started.
Thank you very much for the introduction. I'm happy to be here presenting today. Indeed, my name is Andrew Monroe, Regional Sales Manager here at Radiant Vision Systems, where we build solutions for the automated visual inspection of displays, lighting, glass, and finely detailed products. We like to present on new metrology challenges that our teams have faced in recent projects and describe the approaches that we take to overcome those challenges. And today I'll speak about the increasingly popular pillar-to-pillar displays and the associated metrology challenges that come along with them. Quick background on us. Radiant is a Konica Minolta-owned company since 2015, with global personnel in the range of 300 people. Our large development team allows us to provide turnkey solutions to the automotive industry, whether that be with OEMs, Tier 1s, or Tier 2 suppliers. Our large technical teams allow us to support all scales of projects, from R&D right up to inline production testing. And it's from that breadth of projects that we draw our experience in navigating these metrology challenges. We have direct offices located throughout the U.S., including our headquarters in Redmond, Washington, where our cleanroom facilities are located for manufacturing, Cupertino, and Novi, Michigan. We also have direct offices in Asia to support our manufacturing customers, including Shenzhen, Suzhou, as well as Vietnam and Korea. And we also have staff located in Taiwan and other locations in mainland China as well. In other parts of Asia and in Europe, we have strong representation through our channel partners, shown here in blue. So a quick overview of my talk today. I'll be starting with showing the relevance of P2P displays, though I think we're all aware of their upcoming prevalence. I'll then describe the unique metrology challenges that are present in their quality inspection and the approaches that can be taken to overcome them. I'll then finish with a summary and, of course, time for questions. So pillar-to-pillar displays from a high level. We see them advertised as one of the main features in new and upcoming vehicles, symbolizing how cutting edge the vehicle is. P2Ps accounted for about $36 million in revenue in 2022, but it's the expected growth rate of 46% that shows their significance. And that emphasizes the need to understand and optimize their quality control processes. Numerous market drivers are pushing their growth, some of which are listed here. But foremost is that P2Ps offer a more immersive experience to a market that is very demanding on visual appearance, features, and capability. And really, they're a natural next step in the evolution of cockpit displays. That evolution is outlined here, and it's impressive how far they've come in such a short time. It wasn't that long ago that they just started becoming commonplace in standard vehicles. It's no surprise that since 2005, the trend is toward wider displays, providing more area for more functionality. And that brings us to the large format pillar-to-pillar displays of today and tomorrow. They are, of course, made up of separate component displays. However, the single touchscreen panel that covers them all is what provides the experience of a single overarching display. A number are already on the market, for example in the EQS and Celestic, and many more announced for the very near future. With multiple displays now being viewed by the driver and passenger in one field of view, there are important metrics to be tracked on each individual display to give the impression that it's just one continuous interface. And what are those metrics? Well, many of them are common display tests already: luminance, chromaticity, uniformity, pixel defects, but it's the form factor of P2P displays that provides a unique set of challenges to making these standard measurements. Those challenges include the curvature of the P2P display, its wide aspect ratio, quality between component displays of the P2P, and the quality within each component display. And we'll have a look at each one of these today. Starting with P2P display curvature. It is, of course, visually appealing to have a display that seamlessly follows the curvature of the dash. However, it doesn't come without its challenges in both design and in metrology. Measuring a curved display requires extra considerations beyond those of a flat panel display. And more complex analyses, such as display sparkle, now have an extra parameter to control. So let's consider both of these. To carry out any display test measurement properly, we need to first isolate the active area from the background. The display curvature and its freeform shape can pose a challenge to achieving this. Depending on how extreme the display's horizontal curvature is, we could see an inward bowing effect at the top and bottom of the display in our images. And freeform displays require measurement areas that are not rectilinear. Software registration tools, such as Radiant's RITA shown here, are able to isolate the active area despite these characteristics. These software functionalities employ thresholding, distortion correction, and other logic to isolate the active area from the background each time, no matter what the shape or location in their field of view. An example is shown here, where Radiant's RADA tool detects a keystone and rotated display and properly registers on it as if it were perfectly aligned. Even when the display moves around in the field of view of the colorimeter, it is isolated the same way every time. The next step in a typical measurement process is to remove the inevitable moire that occurs when measuring a pixelated display with a pixelated camera. Analysis of pixel defects and other features cannot proceed if moire is present. We can't remove moire by defocusing, as it obscures small visual details like pixel defects. So we turn to the optimal solution, which is moire removal algorithms that eliminate aliasing while preserving pixel detection capability. These algorithms have been in existence for quite some time, including in Radiant software. However, the display curvature can cause a variation in focus, and as a result, in the aliasing. We must optimize for consistent focus across the display, achieving consistent aliasing so we can successfully apply our moire removal algorithm. Consistent focus is also needed for the actual detection process of pixel defects. Varying focus results in some pixel defects appearing sharply and others appearing blurry. Relaxing our detection thresholds to catch the blurry ones will introduce false defects, such as dust particles or debris being classified as dead or underperforming pixels. So we need to find ways to optimize for consistent focus across the whole curved display. So Radiant performed a study to determine the best ways to do that. And one way is to position the imager on a rotating stage, taking multiple measurements while following the curvature of the display, as seen here. The issue is that this is costly to automate, and is time-consuming, and thus not suitable for production applications where takt time is paramount. A single measurement is the goal. The study showed that the best results came with a high-resolution colorimeter of 29 megapixels or higher, and with a calibrated aperture of f8 or higher. The high resolution allows for enough oversampling to maintain good definition of the artifacts, and the high f number allows for a greater depth of field, and thus more consistent focus across the curved display. Follow-on studies have shown even better performance with ultra-high resolution imagers, such as Radiant's 61 megapixel and 151 megapixel systems. This approach has shown to be successful in our industry projects for overcoming the challenge of curvature in P2P displays. Looking now at the challenge of display curvature on analyses. Sparkle is a common metric of interest for automotive displays, with protocol detailed in the DFF standard. The term sparkle is used to define the effect that is seen when an anti-glare coating unevenly refracts the light emitted by the display. This causes microregions of higher intensity, or luminance, and microregions that are lower, effectively giving the display a sparkly appearance. And while that may sound nice, it's essentially a visual noise to the display and can interfere with the viewer's experience. Historically, characterizing sparkle has of course been done on flat panel displays, and the curvature of P2P displays now introduces a new dimension to the analysis. Anti-glare films and coatings have microstructured surfaces that allow ambient light to be diffused evenly off display screens to reduce glare. However, this surface structure also interferes with the light emitted by the display pixels. Seen here is a display with and without the anti-glare layer. As you can see, the glare is quite effectively removed by the coating, but we also see a reduction in clarity when the layer is present on the left-hand side, and a slight sparkle. This is a result of the anti-glare coating being composed of microstructures that act as small lenses, redirecting the light. It's a delicate balance. We want to optimize the anti-glare layers to maximize the diffusion of sunlight and minimize the impact on the display's output. Objectively quantifying these effects can help us to reach that balance during product development and ensure it is consistently kept in production. Radiant has a turnkey software analysis within the TrueTest automotive display module to streamline this measurement. Most importantly, it contains a well-defined test protocol to both accurately and reproducibly measure sparkle. The main steps of it are shown here in the list. This ensures a consistent measurement across varying batches, display technologies, and form factors. In order to create this protocol, we needed to determine which measurement parameters must remain fixed and which could be variable. We did this by working with our automotive customers to conduct a study across numerous displays, correlating the results back to their human inspection data. The conclusion of our study was that the following parameters absolutely require standardization to allow for reproducible results. Removal of moire, or aliasing, from the measured image, consistent image focus, the correction of any gradient present, the detector size, or region of interest size, in which we analyze the sparkle, and the working distance between the photometer, or colorimeter, and the display. Each of these are already cared for in Radiant Sparkle Test. However, as you can see, consistent focus is a required parameter for successful reporting. And as we've covered, the curvature of today's P2P displays poses a challenge to that. So this adds to the importance of Radiant's recommendation to employ a high-resolution colorimeter of 29 megapixel or higher, with a calibrated aperture of at least f8 when measuring P2P displays. On to the wide format of P2P displays. While it is their greatest draw, it also produces one of their greatest measurement challenges. Their width, of course, must be considered when configuring the measurement system. And they are indeed wide, up to 57 inches horizontal in some models, almost 1.5 meters, as in the Escalade. This is quite challenging when the display is this long in any direction. We know we require a large field of view to measure the metrics of interest to meet brand quality standards. But how do we accurately measure the pixel data of the display when it's this wide? We must have enough imager pixels for every display pixel in order to maintain good statistics and to detect pixel defects. So how do we overcome that challenge? Well, there are two approaches. The first is to again take multiple measurements of the display, zooming in on smaller segments of it at a time to get the proper pixel oversampling ratio. Then, subsequently stitch them together to produce one overall image. This does work, but it's costly to automate, and the takt time is too slow for production. Higher resolution colorimeters can help, as fewer measurements are needed to achieve optimal oversampling ratio, but it's still not ideal. The second approach is to use an ultra-high resolution imager that can capture the full display in one image while providing the proper oversampling ratio. To better explain oversampling ratio, if a camera sensor has an equal or greater number of pixels than the display, then the camera's images can be used to distinguish and measure individual display pixels. If the camera has fewer sensor pixels than the display, it cannot. In this simplified schematic, the camera pixel density on the right should be either equal or higher than the display pixel density on the left for proper pixel level measurement. Otherwise, it means each sensor pixel is measuring multiple display pixels, as in the case of C to B, where 4 display pixels per 1 camera pixel are being measured. This, of course, misses potentially important features on the display. So what resolution do we actually need to measure a P2P display in one image? Well, let's consider an example of a 47.5-inch P2P display with 150 micron pixels. The table here shows the sampling ratio of imager pixels to display pixels in one direction for different resolution systems. The minimum sampling ratio we target for pixel defect detection is 1:1, and we see that a resolution of 45 megapixel or higher is required to achieve that. Ultra-high resolution imagers approach a ratio of 2:1, where the overlap of a complete sensor pixel with a display pixel is more assured. As such, the recommended resolution is 61 megapixel or higher. These ultra-high resolution sensors have shown to be a successful solution to capture an entire P2P display in one image and provide confident display pixel data. Next up is interdisplay quality, ensuring consistent quality between the display segments of the P2P. This plays a large role in the overall experience of it being one single display. Specifically, we'll look at the white point balance of each component display, aiming to align them. We'll also consider the viewing angle performance of each display. Starting with white point. Each component display of a P2P must be balanced to ensure white looks the same on each of them. ISO 12646 is a commonly referenced standard for this, and a pass-fail color region can be created in color space, in which the chromaticity coordinates of white must fall. For this measurement to be successful across all types of displays, the accuracy of a spectroradiometric measurement is required. It provides consistently accurate color measurement no matter what the display technology. The challenge is to capture spectroradiometric data while also capturing the spatial data of interest, like uniformity between each component display. So how do we do that? Well, the first option is to take spectral measurements separately with a calibrated color analyzer. This is done in addition to the colorimeter measurement. The spectral data is used to calibrate the colorimeter's data to the accuracy level of the spectroradiometer, while still providing the desired spatial information. Incorporating the full spectral plot into the calibration, rather than the X and Y values alone, can provide a broader validity range to the calibration. The second option is to use a combined system, such as the Radiant ISC, which is an imaging colorimeter plus an integrated spectroradiometer. Shown here is the 61 megapixel version of the ISC. This combined system takes the spectral measurement immediately after the colorimetric measurement in an exact known location on the display, providing a more accurate correction. It also gives you exact spectral data for every single display in the batch. The combination provides a much faster process and a much more user-friendly experience. So when it comes to uniformity of appearance between display segments of the P2P, such as color, the combined system provides the color accuracy needed for white point balancing, along with the spatial data needed for uniformity. It's also important to consider the vantage point of each viewer as they look across the P2P display segments. The driver and passenger will view each of the displays at different angles, and that must be considered in the design phase. Displays generally have different emission properties when you view them at different angles, For example, the 30 and 40 degrees shown here in the photo. It might be intentional, for example, in a privacy screen, or to avoid distraction of the driver from a passenger display, or it can be unintentional. Either way, it's important to quantify it, so the viewer is experiencing the display as intended while seated in his or her position. This change in display output can be in brightness, for example, the reduction of luminance at high angles in privacy screens, in color, with colors varying in saturation as you move away from the straight-on orthogonal viewpoint, or in contrast, which can be particularly influential on the viewer's ability to see and interpret the data being displayed. So how do we measure the change in these that take place over viewing angle? Well, positioning an imager at each angle of the display is possible, though not ideal. A, it's slow, and B, you'd encounter varying focus across the display. The most time-efficient method is to configure the imaging colorimeter with a conoscopic lens. It employs Fourier optics to capture all viewing angles in one shot, from 0 degrees all the way out to 70 degrees. Exemplary results are shown here for a display with and without a privacy screen. Luminance is expressed in a false color scale, where dark purple is the lowest luminance level and red to white is the highest. In the top row, you can see the viewing angle properties of the display for white and for each of the primaries. On the bottom row, you can see the intentional effect of the privacy screen to minimize signal beyond about 20 degrees. As mentioned, the contrast is an influential parameter on the viewer's ability to distinguish the information being displayed. By taking a conoscopic measurement of the display in the white state and another in the black state, we can then divide one by the other to produce an entire image of contrast. From this, we gain valuable insight into the display's contrast properties, knowing at which angle the user will start to have difficulty interpreting the display's contents. Back to our example of the driver and passenger seeing the center display at different angles, you can note how the driver's 40 degrees, marked by the X on the left, provides him a different display contrast level than the passenger on the right, marked by the right X. Knowing how the performance of each display in the P2P will change with angle, manufacturers can ensure the viewers see the intended brightness, contrast, and color from each display. Radiance imaging colorimeters can be configured with a conoscopic lens, creating a turnkey solution to measure viewing angle characteristics of each component display in a P2P. It's fast, capturing all angles in one image, and has produced valuable insight for our customers during the design phase. Lastly, we'll look at intra-display quality, or the quality within each component display of the P2P. Here, we'll focus on emissive displays, as they are becoming more and more common in automotive installations. With any automotive displays, whether LCD, OLED, or other technology, we have a common set of quality parameters. There are many standard display tests for automotive displays, which can include those listed here. Increasing display resolution can increase the difficulty of measuring these parameters. Higher resolution measurement equipment might be needed. However, the biggest additional challenge is presented when emissive displays are used in the P2P, and that is indeed becoming more and more common. In 2022, OLED made up just 3% of automotive displays, but is projected to grow to approximately 17% in just 4 years. As seen here, many of the upcoming P2P displays are set to implement emissive technologies, so ensuring their performance is of significant importance. The performance advantages brought by emissive displays, which include wide color gamut, true blacks, and low power usage, are accompanied by additional challenges since they are composed of individual emitters that naturally have variation in their output, and that can be apparent to the viewer. The non-uniformity can be both in luminance and in color. The illustration here shows an exaggerated example of how the peak wavelength of LEDs within a display can change from one to the next, producing a variation in color that is noticeable. Here we see a different green between LEDs across the display. Luminance level also varies between LEDs when driven at the same current, producing the luminance non-uniformity, or Mura, shown here in the before image on the left. This is a measurement we conducted on an OLED display, and you can see the variation from pixel to pixel in this image, where every pixel represents an LED in the display. This results in a non-uniform display that must undergo a correction process before deployment. To perform this correction, we must accurately measure the luminance and chromaticity of each emitter and produce a scalar correction for each one to even them out toward a common target. This process is called demura, or removing the Mura from the display. So how do we do that? Well, we do it by using a high-resolution imaging colorimeter, such as Radiant's 61 megapixel Prometric system, providing sufficient oversampling of the display pixels to yield highly accurate data for the correction. Radiant's portfolio includes a range of lenses, from wide-angle down to microscope optics, as seen on the bottom right, to ensure we can meet the field of view needed for the display being measured. For the solution to be turnkey, the high-resolution colorimeter should be paired with purpose-built software that generates the correction matrix from the pixel data. Traditional approaches using a blob tool can be too computationally intensive, as it has to find and isolate millions of LEDs, and this results in slow or unsuccessful reporting. Radiant's TrueTest VisionCal software was developed to provide accurate correction fast, meeting the needs of high-speed production lines. From a high level, the workflow looks like this. Using our blob tool, register on the emitters in the four corners of the display to determine the display edges, as we see in the top right images. Since we know the pixel pitch, we can then place a region of interest, or ROI, over each emitter in the display. Here we see the isolation of all green emitters in the bottom right image. Then measure the luminance and color of each ROI. It's critical to have enough of our pixels here to do so. 61 megapixel is a minimum required in all of our recent projects. Then compute a correction factor for each ROI, or emitter, that balances the output of each toward a common target. When those correction factors are applied back to the display controller, we see results such as these, taken from recent projects. Here we used Radiant's Prometric 29 megapixel and 61 megapixel imaging color emitters to accurately measure each emitter's output, and our TrueTest VisionCal software to automatically generate the correction matrices. On the top left is an example of a micro-LED display, before and after correction, showing easily visible improvement in uniformity. On the bottom left, we have an example of a fall display, showing full blue, and the luminance across the display is shown here in false color. We see an approximate doubling of the uniformity upon applying the correction matrix, which in the case of a fall display is a zoned correction, since you can't control each LED individually. The uncorrected display had a delta of 40 nits between the min and max luminance showing, represented by red and white respectively. And the corrected display had a delta of just 5 nits, showing as different shades of green. On the right, we see an example of how the correction process also enhances color uniformity. Each dot here in color space is for an area on the display whose color was measured. Before correction, we can see a variation of approximately 0.025 in CX and CY. The correction process reduces that down to just 0.005. Employing these corrections, manufacturers are able to provide the uniformity and intra-display quality needed in the component displays of a P2P. Looking ahead, in the world of automotive displays, the landscape is always changing. Technologies progress at a fast pace, and it already seems that P2Ps are no different with the emergence of P2P head-up displays. These are full-width head-up displays that occupy the lower portion of the windscreen, projecting information that is relevant for the driver and passengers. They employ a dark coating as a background, and then project high-intensity images to create the necessary contrast for visibility in a variety of conditions. Despite being a different technology, many of the same P2P measurement challenges apply. For example, it is an equally wide format. There is a curvature, the windscreen. Viewing angle will vary for each of the observers, and so forth. The performance metrics we track can be different, however. Some are carried over, such as uniformity and contrast. However, image quality metrics like ghosting, distortion, and MTF are also of interest for virtual and projected images. The SAE J1757-2 standard is commonly referred to as a basis for this type of testing, detailing the protocols to follow. As we focus further out on the image plane, achieving clear images at relatively small scale requires greater image resolution. Capturing images as far as 20 meters away means evaluating more visual details at more precise coordinates. If details are missed, this can impact the accuracy of our measurement. An imaging system should match or exceed the resolution of the HUD projection to ensure that the projection is evaluated in the exact same detail as it is produced. This is especially critical for image clarity testing using MTF, and can also be important for characterizing distortion, warping, ghosting, and other defects. The electronic lenses paired with radiant photometers and colorimeters provide the flexibility needed to work at numerous focal planes. Both focus distance and aperture are controlled via software, allowing automated measurement at different virtual image distances without the need for manual intervention. They even allow for the ability to confirm the virtual image distance of the head-up display. Ghosting is a phenomenon of misaligned images on the internal and external windshield surfaces. The viewer will see a lower luminance duplicate of the original primary image, and this is of course undesired. Ghosting can be characterized by projecting an appropriate test pattern, for example, a dot or line pattern, to track geometric location of both the primary image and any ghost images present. The ghost may be connected to the primary or may be separated. Shown here is an example where the ghost is separated from the primary. Radiance ghosting analysis has registered on each primary dot, as well as its paired ghost, numbering each of them appropriately. We then report out the displacement between the two, as well as the luminance ratio in the results table, as shown on the lower left here. This data objectively quantifies the ghosting present and allows for subsequent steps to be taken by the designer to minimize or eliminate it. Distortion is another parameter that must be quantified and corrected in a virtual or projected image. Standard dot or grid patterns are projected, and ideally they would maintain their integrity. However, in reality, they will almost surely be distorted. For example, rotated, displaced, keystoned, or the spacing between dots or grid intersections will no longer be equidistant. This must be characterized and corrected when the HUD is implemented into the vehicle. Radiance distortion analysis is able to automatically quantify distortion metrics according to the specifications of many OEMs. This includes reporting data such as angular displacement, aspect ratio, trapezoid, smile, and many other types. This can be done offline at the component level or can be implemented as an inline process following HUD installation. The distortion data is used to generate a correction matrix that is fed back to the controller, resulting in a distortion-free image. These types of testing and corrections are likely to be implemented into QC processes as P2P head-up displays continue to mature. So that encompasses the main challenges and solutions we've encountered in our recent projects working with P2P displays. To summarize, For the challenge of P2P display curvature, the recommended solution is to employ a high-resolution imaging colorimeter of at least 29 megapixel with a high iris setting to optimize depth of field. This enables a successful measurement in one shot, providing the cycle times needed in production applications. For the challenge of P2P wide aspect ratio, the recommended solution is to employ a high-resolution imaging colorimeter capable of providing the necessary sampling ratio of 1:1 or more. This ensures the ability to properly detect pixel defects while measuring the entire P2P display in one shot. 45 megapixel is a minimum, with 61 megapixel or higher being recommended. For the challenge of inter-display quality, the recommended solution is to employ a combined system of high-resolution imaging colorimeter and integrated spectroradiometer. This provides the color accuracy needed for white point balancing, along with the spatial data needed for uniformity. Viewing angle characteristics for each component display can be measured during the design phase, for example with a conoscopic lens, to ensure the proper viewer experience when looking from their vantage point. And for the challenge of intra-display quality, the recommended solution for each component display of the P2P is to perform accurate pixel-level measurement, followed by generating a D-Mora correction matrix to even out non-uniformity between emitters across the display. This generally requires at least a 61 megapixel imager to accomplish, along with a purpose-built software module to facilitate the process and ensure accurate results. Thank you very much for your attention throughout my presentation, and I'd be happy to take any questions.
Thank you so much for that great presentation. And now let's get to the Q&A. We have some questions that have come in from the attendees, so we're going to move into answering those right now. Now for our first question. For display sparkle, have you seen variation in the results for curved displays versus flat displays? Andrew?
Thanks for the question. We, in fact, repeated the original sparkle study we performed on flat panel automotive displays, but on curved automotive displays to see if there was a notable difference. We know from the original study that we need to control and keep consistent the 5 parameters covered in the earlier slide, which include removal of moire, consistent image focus, the correction of any gradient present, the detector size or the region of interest size, and the working distance between the colorimeter and the display. The study found that if we follow the procedure using a high-resolution colorimeter and a calibrated aperture of f8 or higher, and that's in order to achieve a greater depth of field, then we see a deviation of just 2 to 3% from results expected from flat panel displays. It is important to follow the test protocol tightly, of course, I should mention.
Great, thank you for that. Okay, now here is our next question. You said your solutions for calibrating emissive displays like OLED is faster than a blob tool. How are you different from a blob tool?
That's a good question, thanks. We've been implemented in emissive display correction for many years across a number of different display technologies. So our solution is quite mature. It incorporates techniques to optimize the accuracy of measurement and correction that are unique, coming from experience in this space. Those include accounting for the distortion in the measurement system, measuring and accounting for the viewing angle effects present in the measurement, working effectively when resolution limited, meaning that we have functional solutions when we don't have as many sensor pixels as we'd like across a display pixel. Here we would use approaches such as our space pixel method or our fractional pixel method to ensure accurate measurement when other tools such as a simple blob tool would fail. Our fixed grid registration technique also produces a more accurate measurement as we ensure to measure the entire emission of the LED. Blob tools will depend on thresholding to isolate the LED from the background, which will inevitably miss some luminance in the measurement. And as mentioned earlier, our approach is significantly faster than a blob tool, which is a large value add for production applications.
Excellent. Thank you for that. And thank you for that question. Thank you for all the questions so far from the audience. It looks like we have one last question for today. However, if we didn't get to your question for whatever reason, we will reach out after the webinar is over. And if you still have any last questions or comments, we'd love to hear from you. You can add that information now to the Q&A box on your screen and click submit. Again, we have one more for today, but if we don't answer you today, we will reach out later. Okay, but for now, here's our last question for today. On slide 63, you showed a test pattern for testing ghosting that had both dots and lines. Why have both? Aren't only the dots needed?
Thanks for asking. Yes, you're right that ghosting analyses do not require more than one shape in the test pattern. In fact, what I showed there was a composite pattern of dots and lines, which we used to simultaneously test for both ghosting and distortion. The dots in the pattern are used in our distortion analysis, and the lines are used for the ghosting analysis. So this allows us to take one less measurement, saving on cycle time. Our software does have the capability to execute the test schedule asynchronously, meaning that it will take a measurement and can begin performing the analysis on it while also capturing the next measurement. You can line up multiple analyses to take place on the same measurement, such as ghosting and distortion on the same composite pattern.
Excellent. Thank you for that. And that was our last question, so we are going to wrap things up right there. So once again, Andrew, thank you so much for taking the time to be with us today and also taking the time to answer some questions from our audience. Take care, and we will talk with you soon.